This conference will now be recorded.
So good morning, and this is the Yaskawa Wednesday IQ training class. We're going to speak today about an update in the situation in California on harmonic distortion compliance, the overriding specification being IEEE 519-2014. We will also be talking about some harmonic analyzer programs, I should say harmonic estimator programs, as differentiated from a full-blown analyzer program, which is far more accurate and far more expensive. But the harmonic estimator programs are readily available. They're free, they're easy to use, and they'll get you within 5-10%, which is enough to make some economic decisions with regards to your application. The other thing we'll talk about today is an update on the matrix driver supplied to submersible pumps, and we'll go into a little bit of an explanation on how we've determined which filters to use and which filters not to use. It does result in significant price savings on the filters as opposed to using a full voltage traditional variable frequency drive on a submersible pump. So with that, the harmonic distortion update. Craig, if you would you please go over the terms of the present PG&E energy savings rebate specification?
Okay, PG&E's starting to clarify the tier levels, and right now tier 1 rebates, you can get any PPC3 panel will fit the specification, the ITRC specification. Tier 2, which is where we've been battling them because they didn't want us to use outside filtered air to cool the cabinet, they've relinquished on that now. And so now for tier 2, all of our PPC3 units with an input or harmonic filter classifies for that. But of course, when you get into that, then you start looking at the matrix technology. And then tier 3, we're still fighting with them because they're still prohibiting the use of cooling valves with filtered air. So they're asking for auxiliary or alternative cooling methods, which basically boils down to a heat exchanger or an AC unit, which now makes the site cost prohibitive. We haven't figured out how to pencil out a tier 3 one yet.
What's the difference between tier 2 and tier 3 other than that?
They basically say that you need to have a front and back end filter, versus tier 2 is you only have to have a line reactor, you have to have an input device that is going to filter to IEEE 519 specifications.
So if I may clarify, the tier 2 and tier 3 both require IEEE 519 compliance on the input, and tier 3 requires an additional output filter?
Correct, and no filtered outside air cooling.
And the reasoning for requiring the output filter?
Dr. Burt just threw that in there.
Because that doesn't seem to have any effect on energy savings. In fact, it probably adds to the parasitic losses because it's an extra filter.
Exactly, and that's where we get into a question of overstepping what was supposed to be guidelines, they're called specifications, rigidity on that, because we've tried to tell them the same thing. It's not something that is commonly done in the industry, but he doesn't care. He wants to do it because he wants to do what he calls an enhanced panel, which would mean that's the Cadillac system that any rancher could grab. So that's what he wants.
Okay. Well, it is what it is. I'm glad to see that they have modified the original tier 2 specification to allow filtered air, because every pump panel from us, Danfoss, ABB, and anybody else that I can think of uses that.
Yeah.
I
So we've
think
got them to understand that. We've submitted a lot of pictures to them, things like that. PG&E is actually the one that overwrote that over ITRC. Dr. Burke fought that one.
good for them. Dr. Bird is B-U-R-T?
Yeah, BURT.
Okay, so that's good, because use of air conditioning, as we have all found, is not a more reliable system. It's a single point failure. It's a complicated system that in many cases is not suitable for the outdoor environment. I think we at Yaskawa will stand on that because our NEMA 3R filtered air systems have been in use now for over a decade and have exhibited extremely good life, and our competitors have a similar experience because that's their main offering. Craig, when was the last time you saw an air conditioned panel in the agricultural world?
It's been years.
So,
The one I saw, the air conditioner was disabled, and they'd gone and bought a Walmart air conditioner and threw it up on one side of it.
oh, that's funny. Okay, well, I'm glad that we have an improvement in the PG&E energy rebate specification. The meeting that you are the meetings that you're monitoring, I think you made a very good statement the other day, and I'm going to repeat it here. The first step towards getting better power factor on the grid, which is what PG&E is recognizing and stating as their goal, is the carrot, which is their rebate specification. But inevitably, once they achieve whatever goals that they can achieve through the carrot, if they still want to achieve harmonic distortion compliance, and therefore the power factor goal that they have for the overall grid, if they can't achieve it through the energy rebate mechanism, then they'll turn away from the carrot and add the stick, which is mandated compliance. We've seen that in other areas. State of Washington is the example I always cite because it's close to California, but we see it in many other states in the United States, and frankly, we see it much more frequently in the rest of the world. Compliance to whatever the total harmonic distortion and displacement power factor standards are. In the United States, again, it's IEEE 519-2014. In Europe, it's an EN standard. There's an ISO, or International Standards Organization, version of the EN standard for the rest of the world. We need to concern ourselves with IEEE 519. Bottom line is, if you read through all the paperwork, you need to have a 5% total harmonic distortion on the current and voltage waveforms to comply with IEEE 519-2014 at the point of common contact, which is typically the secondary of your feed transformer. That would be the transformer that will drop you from 12.5, 13.8, whatever the supply voltage is off the utility, to the 460 volt or 230 volt that your particular facility uses. It would be the power pole transformer, for example, on a single point pump installation in a rural area. It would be the main transformer for a building in the case of an industrial facility. So, point of common contact compliance, and they're getting serious because they have to. This is not an option for the power companies. The only option for them at this point is how late they're going to be in coming to the table. The fact is that the grid has significant issues, and this is a good way to correct those. Now, what I want to show you today are some tools that you can use to begin to become familiar with how to estimate your own harmonic distortion so that you can make some economic decisions and some engineering decisions in terms of what you're going to use on your particular installation, whether you're retrofitting, upgrading, or installing new. I'll start with the Yaskawa harmonic distortion analyzer. We make one specifically for the IQ product. We also have an industrial one. These are downloadable for free from the website, and they're useful, they're easy, but as you can see there are some limitations, and therefore I'm going to introduce you to some other harmonic distortion estimators. Again, bear in mind these are estimators. If you want an accurate analysis of an existing system, use a harmonic distortion analyzer. Hook it up to your system and measure it. Use the Fluke or the Dranitz product. These are not cheap products. They're $3,000-$4,000, but they do excellent analysis of the distortion and of the total power factor. The advantage of measuring real time is obvious. The second most accurate way of doing it is to buy one of the analyzer software programs, which require a certain degree of competency to use, and they will give you a much more accurate analysis of your particular installation. It's called the single line diagram analysis. And I would say that, single digit accuracy for the analyzer programs, double digit accuracy, 10 to 15% maybe on the estimators. So with that, I'm going to share the screen and show you a couple of programs that are very easy to get. This is the harmonic distortion analyzer from Yaskawa, and you can start with a new project. These are designed to give you a very nice printout of your analysis. They have been accepted in many cases in terms of documenting the installation, both in terms of compliance to engineering specifications on municipal projects, as well as submitting to authorities. That's at the discretion of the authority, so I'm not going to say it's always going to be accepted. So we start the project down here in the lower right hand corner, and you can fill out all that information. We won't do that today. This is a simple demo. Here's where you define your utility and service transformer data. This is critical. PCC in red here is the point of common contact. That is where you're going to hang your analyzer, connect your analyzer to determine compliance, because this is where IEEE 519-2014 requires compliance. They don't require it on the individual components that are downstream from this point of common contact. They're interested in the point of common contact, which can also be stated to be the interface between the private user and the public utility. IEEE 519-2014 is aimed at protecting the grid and maintaining the quality of the waveforms on the grid. Therefore, they want you to comply here, and what you do downstream of that, in order to comply, you have a relative degree of freedom to do so. So, in the Yaskawa program, if you specify the kVA and the voltage, we will pretty much estimate the impedance for you. Now, this is how you add systems to create your single line diagram so we can analyze it. It's basically everything that's hung on the point of common contact. So what you're doing is you're defining everything represented by that little square there, or everything that would be connected to that little square or rectangle. So here we are. We have 18 pulse, 12 pulse, 6 pulse systems. The 6 pulse system is the standard drive with no filter, and 12 pulse and 18 pulse systems are using static harmonic distortion filters. We do include a matrix option here. We also include the ability to add linear load. Linear load in your single line diagram helps the harmonics. So if you have say, 4 300 horsepower VFDs and one 500 horsepower motor running across the line, you certainly want to add that 500 horsepower system to your single line diagram because it helps the harmonics. The ability to add in this particular program is down in the lower left hand corner, and that's the add system. So here we go, and then you have your linear load, or you can select an IQ Pump 1000, which is the standard 6-diode bridge drive, or you can select an IQ Pump matrix, which is designated by the U. In the case where you have 12 pulse and 18 pulse systems, you can add those in. They're rare in the agricultural world. They're very common in the older installations in the municipal and utility world. Note that we do not have options for active front ends and for other static filters offered by companies like MTE and TCI. This, in my opinion, is a downfall of this program, and therefore I only use this program aware of its limitations. When I have these other components that I have to use that exist, for example, in a system that I'm trying to analyze, I go to a different program, which I'll show you in a second. So here we are. There's the single line diagram. These are your options, and this line up here represents the drop-down menu that you saw on the previous screen. And note that when you start adding things, we start incrementing these totalizers at the bottom for each type of load. Right now, obviously, we have nothing specified. So blue is the total horsepower, and the impedance of the system is in white. Again, 0 for all the horsepowers because we haven't specified anything. And then you get this report, which gives you a compliance, no compliance here, and then your actual distortions. Now, let's take a look at another program, and that would be a program that looks remarkably similar to the one I just showed you, and that's because the same guy wrote it, a fellow by the name of Bart DeFries down in Florida at what is Bart's company name? I'll have to think of it. But at any rate, Eaton has a different implementation of the available components. So we start the project, we fill out the information, same screens for the transformers. And by the way, you can download this from the Eaton site. If I haven't already, I will send you an email with these links. I haven't sent it yet. Okay, I'll send it as soon as I'm done. Now, here's a help screen. No systems defined. Again, the add system button, and note a lot more options. This is the one I use when it's not strictly a Yaskawa system. So let's go over the options that are available. Obviously, the linear load is the same. Any motors hooked up with a contactor. You have your 6 pulse. You have a 6 pulse with a 3-put input line reactor, 5-put input line reactor. Sorry, 5% input line reactor, 5% DC link reactor, which is called a bus choke. It's also called a DC link choke, and then etc. Different combinations. So a very much more complete implementation of this program. Most importantly, it has active front end, which is a general classification for non-static, active, transistor-based harmonic filters that point back to the line. The matrix is a type of active front end this gives you the ability to also specify an ABB ULH or a Mirus dedicated purpose input active filter. That isn't a drive, it's just the front end that points to the line, and then it supplies power out to all the other drives of any brand that you happen to connect to the Mirus output. Mirus is one of 20 companies that I'm aware of that make active front end filters only. They don't make drives. They're in the business of cleaning up the noise that drives create, not through static filters, but through an active filter. If there is a spike on the sine wave, voltage or current, these active front ends are fast enough to fire the negative equivalent of that spike and neutralize that spike. That's the theory behind active front end. So, onward to the more traditional ways of handling harmonic distortion filtering, which are the multi-pulse transformers. And you can see that this program gives you more options in that regard. So look to the link on the email that I send you. The Eaton system, I think, is, with respect to Yaskawa, much more useful. Now, while we're in this, I want to again show you there's the report, but you have the same options as you have in the Yaskawa program to create paper, email, PDF versions of these to use in your documentation for the system and to use in your submittals to the necessary authorities and colleagues that need to have this information. Very convenient programs to use. In the coming weeks, as I research more and more of them, I will be sending you more options for harmonic distortion analyzers. I think the more the merrier in this case. You decide which one you want to use. Bear in mind we're in a 10 to 15% accuracy here, so it's an estimate, and that's why they call them estimators. But they are very useful in making us aware of just how good or bad the system is that we're working with. Now, I will also send to you in the email subsequent to this recording the presentation on the differences between IEEE 519 1994 and IEEE 519 2014. That's a redux of a class that we've done twice already this year, and it's just a good presentation to have to review the context of these harmonic analyzers. Given the fact that PG&E is obviously making moves, and they're making moves at what can only be described as a rapid pace compared to their glacial pace of the past, I can anticipate that Southern California Edison and San Diego Gas and Electric will follow suit, as well as some of the smaller utilities. The fact, again, that I stated it earlier, is they must do this. If for no other reason, harmonic distortion and poor power factor on the grid heats up components. If we're heating up transformers in the middle of a forest or a forested community, we start fires. I think these utility companies have gotten severe bloody noses from these fires. They've been sued to death. PG&E, I think, declared bankruptcy. I stand to be corrected on that. So you can see that they're now highly motivated, and therefore this becomes a commercial reality for us. And therefore we should be prepared for it. Now, on to the second subject of this recorded session. I want to show you an update in the mission that we have to try to improve the reliability of submersible pump installations when used with variable speed controls, the variable frequency drive. I give you frequent updates on this because there's a lot happening on it. The most recent situation that I have had has been an engineering analysis based on a specific job at one of the cities in the Los Angeles area, where the engineering firm, an outfit out of San Luis Obispo called Canon Engineering, specified the Yaskawa matrix drive. The submersible pump companies have experienced significantly lower reliability on their products when applied to drives. This is something that's been happening over the last 10 to 15 years. Their after-sales costs in terms of warranty and service have gone up significantly. This has motivated them to try to take action to understand and correct the situation so that they can improve their reliability, increase their customer satisfaction and the uptime of these critical systems, many used to irrigate crops, and of course to stop the bleeding on the after-sales costs. Grundfos and Franklin have come out stating that they require filters on the output of the standard 6-pulse constant voltage DC bus 6-transistor inverter bridge VFD. Probably 90-95% of what's out in the market right now. This is because they have two issues with the VFD as opposed to sine wave power coming directly from the utility to their submersible pump via a contactor. The VFD used instead of the contactor gives variable speed capability, therefore the ability to monitor and maintain pressure, flow, tank level, what have you, but damages the submersible pump to the point where it doesn't last as long as it should. 2 points of damage: one, voltage spiking from the output of the VFD; two, the harmonics on the output waveform. We're talking output waveform here, not input waveform, but harmonics being defined the same way, the distortion of the sine wave shape. That sine wave shape, being imperfect, causes thermal stress in the submersible motor. Craig, you want to elaborate on that a little bit, because you're very much the expert on this?
Okay, on the thermal stresses on the motor with the harmonics, especially on submersibles, we've discovered that what harmonics do is different harmonics cause the motor to react differently. Basically, it puts the motor into either a forward state, a no torque state, or literally a reversing state, all happening while the sine wave is being created and the harmonics are reacting with the motor. So all this causes the motor to heat up. And then we throw on top of it a couple hundred feet of water column, and it causes the motor to do what we call a torque ripple. And because of the torque ripple, the motor overheats, and that's why my personal opinion is a lot of their motors are overheating because they're being stressed because of the way they're being designed nowadays. And that's a whole different subject. But in a nutshell, that's pretty much the harmonics causes the inefficiency of the motors to be exacerbated.
So let's take the sine wave shape first. This is the output of a matrix drive to the submersible pump motor. This is the actual oscilloscope picture of that. This is actually a video, and I'm not going to play it right now, but it is proof positive. This is the waveform going to the motor in terms of output current. This is the waveform going to the motor in terms of output voltage. And here are your input voltage and input current. They're sinusoidal, they have low harmonics. In the case of the input It's compliant to IEEE 519 down to 30% of load. No filters. And a little parenthesis there, there's an EMI RFI filter which is on there to take emitted noise away to comply to the FCC standards, but it has nothing to do with our harmonic distortion compliance. And on the output, again, we have a good sine wave, which is what the submersible motor wants. The submersible motor was originally designed to take the utility power, which looks like this. And you can see that we look very much like the utility power, even though we've inserted this big digital switching transistor box. And we now have variable speed capability with a digital simulation of the sine wave that is much better than the original drives. Now, if we look at an original drive waveform to the motor, and bear with me while I try and find one of those, because I just had it up. Nope, that's not it. The bottom line is that the VFD basically puts out a constant voltage approximation using pulse width modulation only, and as a result, it has a very poor waveform to the motor in terms of harmonics. Okay, so no, that's not it either. All right, well, I'm going to have to use that as an example. It's not exactly what I wanted, but the pulse width modulated waveform looks like this. It's square waves, and it's not sinusoidal, obviously. When you look at the waveform output of the matrix drive, which is here, you can see that, and this is not a good example. Let me go back down to where I was before. You can see that it is much more sinusoidal. It's not perfect, but it does result in an almost perfect current waveform. We can depend a little bit on the filtering of the inductive reactance of the motor winding to smooth that out. This is what will determine the thermal impact of the VFD on the submersible motor. Because our current waveform, due to our superior voltage waveform, remember that the VFD, the standard VFD, basically has full height switching. They don't have this nice curving to simulate the sine wave. Their current waveform to the submersible motor as a result will be less sinusoidal, will have more harmonics in it, more distortion, and therefore, as already has been proven, they impact this motor with more heat. So, voltage spiking and heat. The voltage spiking issue, matrix versus a standard drive, we do not completely cure that. What we do is reduce it, and that's because we do not always switch from a full voltage DC bus. If we're always switching from a full voltage DC bus, we will always be switching in a 460 volt AC input application, roughly 700 volt pulses to the motor, and the leading edge spike can be as high as 1400 volts. So we are hitting that motor at a minimum 2,000 times a second with 1400 volt spikes. And that's because we're always switching from the constant voltage DC bus. With the matrix drive, we are not always switching from the constant voltage DC bus. We are switching directly from the line, and therefore we have other choices in terms of the voltage span, the voltage height of the pulse. based on the relationship between phases of the input AC coming into us. We take input AC 60 hertz from the power company. We choose what, at any given instant, any of 3 different voltage spans, and we fire that into the motor based on the sine wave frequency and voltage we're trying to create in the motor. We've got more choices than one DC bus voltage. It's certainly a more sophisticated approach, requires much greater capability in the software, but remember that the original constant voltage drive, the constant voltage DC bus drive, was developed in 1983. I think between then and now we've developed a bit more in terms of processor capability as well as the ability to develop software to do these more complicated functions. The reality of it is that in today's world, this is child's play. And the matrix drive, as a result, gives us these advantages with extreme reliability. So the ability to choose more than one voltage height at any given moment, as opposed to only having the option of 700 volts, means we, at some points, will still put in full span voltage to the motor. So we will hit the motor with a 700 volt pulse, but at most other times we're less than 700 volts. With that said, the argument could be made that we don't need as much of a filter. And do we need a filter at all for the voltage spiking? Because this voltage spiking issue is death by 1,000 pinpricks, and therefore if we're hitting the motor with 2,000 full voltage 1,400 volt spikes versus 100, the motor insulation will last longer, obviously, in the case where we have a lower cumulative number of high voltage spikes. Nevertheless, the commercial practicalities are that DVD-T filters are made en masse in production volumes for constant voltage traditional VFDs. To make a custom one for a matrix drive would actually be more expensive. And to assume that we don't need a filter is probably a little bit more aggressive than we at Yaskawa wish to take in terms of a technical position. So what we are saying is use a DVD-T filter on the output of a matrix drive to be certain that the voltage spiking will not damage the motor winding. However, because our sine wave is accurate in terms of the current waveform, again I'll refer you back to this presentation here, where our current waveform is sinusoidal, we are taking the position that we do not need a matrix. We do not need on a matrix drive a sine wave filter. The sine wave filter is vastly more expensive than just the DVD-T filter. A good sine wave filter is a DVD-T filter also. So we're not saving the full price of the sine wave filter, we're probably saving 3/4 of it. So the economic benefit is still tangible. I recently went through a submittal process where the city that I mentioned in Los Angeles had specified a certain submersible pump company. I believe it was Hitachi. The winning contractor submitted a different submersible pump from a company called National Pump in Arizona, who happens to use a submersible motor manufactured by a company that I believe is in Australia. And the reason that I believe that is because in the engineering discussions that I had with the motor company, the engineer was in Perth, Australia. So we're talking to him at early morning our time, and it was 11 o'clock p.m. his time. I'll be quick on this, but the summation of that analysis was that the submersible motor company agreed and wrote a letter to the city stating that they would honor their warranties with a DVD-Q filter, but they were not requiring a harmonic filter because after analyzing the data that I had submitted to them on the Yaskawa matrix drive, they were satisfied. So I believe this will be the trend moving forward. We're certainly going to try to approach Grundfos and Franklin and see what they have to say about the matter. Right now they are, Greg, I guess the proper term is strongly recommending a full-blown sine wave DVD-T filter on all VFD applications. Is that correct?
That would be correct.
So they're not really differentiating yet on the matrix drive, and nevertheless, that's the update on that situation. We think it will go in this direction. If through several of these projects in the municipal area we have been able to prove that using the matrix drive without a harmonic filter but with a DVD key filter is safe enough that the manufacturers of the motors are willing to write letters stating they will uphold their warranty, we think that's a significant step forward. So, with that, we've covered the two subjects that I wanted to cover today, and I will be sending out the email with the harmonic distortion harmonic distortion estimator programs. The harmonic distortion analyzer programs you're welcome to buy. They're $1,000, $2,000, and of course the hardware tool to take an actual reading, whether it's a fluke or I don't mean to say that fluke is the only one that I would recommend. Dranitz is another one, and I'm trying to think of the other competitor to fluke, which I can't think of. I'll apologize in advance for my bad memory, but those devices are in the $2,000 to $4,000 range to have an actual set of high voltage probes that you can go and connect to your system and get a real reading. A harmonic distortion analyzer is basically an oscilloscope with a bunch of firmware on it that allows it to analyze the data of the sine wave coming in on the oscilloscope. But at the end of the day, it's an oscilloscope, and oscilloscopes are not cheap. So, with that, I want to thank you for your attention. I hope this recording will be useful to you. Please note that the following email that I'm going to be sending will have the estimator links. We'll have a presentation on the present IEEE 519 2014. And with that, it's 8 o'clock. Time to go to work. Thank you very much.
Thank you.